Human language is messy. We communicate using sarcasm, double meanings, and slang that shifts constantly by the week. Computers, by contrast, are rigid. They only understand the unyielding absolute logic of mathematics. Yet today, we have machines that translate complex dialects in real time and compose structured Shakespearean sonnets on command. To bridge that gap, data engineers didn't try to teach machines English. Instead, they translated the human vocabulary into pure, calculable geometry. An AI system does not comprehend the words you are hearing right now. It calculates them. The first step in making that possible is figuring out how to turn a written alphabet into a string of digits. You cannot feed a word like apple directly into a neural network. If you push raw letters into these mathematical equations, the system will immediately crash. The initial fix is tokenization, chopping a raw sentence into discrete pieces, like individual words. Once divided, the computer assigns a unique ID to every single piece. The phrase, "I love pizza," becomes a linear array. I is 14, love 902, pizza 55. The machine can now process the data, but the numbers 14, 902, and 55 represent arbitrary quantities. The computer has no way of knowing that pizza is a food, or that love is an emotion. A flat list of numbers leaves the system blind to meaning. To solve this, researchers stopped treating words as random items on a list. They introduced a technique called word embeddings. Word embeddings is a mathematical method that gives each word physical coordinates in space, allowing the computer to map relationships between concepts. This graph plots concepts on two axes, horizontal gender and vertical royalty. Man sits bottom left, woman bottom right. King and queen keep that exact left-to-right gender gap, but are elevated to the top. The geometric distance between both pairs is exactly identical. The computer still lacks a human definition of queen, but it resolves the concept by solving a literal geometric equation. If you take the coordinates for king, subtract man, and add woman, the resulting vector lands precisely on the coordinates for queen. A two-dimensional graph works for a simple example, but mapping the entirety of the English language requires a massive jump in scale. Real models plot words across thousands and simultaneous axes, mapping abstract variables like temperature, size, color, and emotion. In this vast multi-dimensional space, analogous words naturally group together. Dog, puppy, and hound end up tightly clustered in a specific neighborhood of coordinates. When you ask an AI to write a story about a dog, it navigates this mathematical galaxy. It selects consecutive words like bark or leash because they physically hover closest to the current topic in the coordinate space. What looks like thinking is actually a machine calculating the shortest geographic pathways between mapped concepts. There is a limit to this spatial map. The system faces a collision when human language uses the exact same word in two entirely different ways. Consider a sentence describing someone eating a juicy apple while checking the time on an Apple Watch. One is an organic fruit, the other is a tech corporation. For a basic geometric model, this creates a failure. The word apple possesses only one fixed set of mathematical coordinates. The machine cannot differentiate between the fruit and the company. Static spatial geometry fails when a word's definition changes based on its surroundings. Mathematical location alone cannot account for the nuance of human context. To fix this, engineers needed a system where coordinates could shift. The model had to analyze every word in a sentence simultaneously to decide where a word like apple should sit in that specific moment. In 2017, Google researchers introduced the transformer architecture. It relies on a mechanism called attention. Attention is a mathematical process that assigns weights to surrounding words. If the word juicy appears nearby, the system pulls the coordinates for apple toward the cluster of fruit, away from the tech companies. This dynamic remapping allows modern models to maintain a coherent topic over thousands of words. By calculating how words influence one another's position in space, AI transitioned from a static dictionary of numbers to a system that tracks the fluid, shifting relationships of human language.